Okay, welcome. This is Physics 1020 and 1090. This is a lecture for Wednesday, March 18th. We're talking about Chapter 24, Wave Optics, and this is the second video from this lecture discussing polarization. We have light has two polarization states. Now, what does that mean? Well, we talked about light earlier. Light is an electromagnetic wave. It has an electric field which points in one direction and a magnetic field perpendicular to it. And the whole thing propagates in this direction with the speed of light. Now, it turns out that light is a transverse wave. The electric field points perpendicular to the direction of motion. But you know, there's two directions that are transverse to the direction of motion. You can have the electric field going up, down, and the magnetic field going, if you looked from the end, left, right. Or you can have the electric field going left, right, perpendicular to what it was over here. And the magnetic field going up, down. Electric field goes left, right, and it propagates in the direction. So there's now two polarization states to light, corresponding to the direction of the electric field. We'll focus on the direction of the electric field instead of the magnetic field. So what does this mean for light? Well, first of all, let's imagine you looked at that light ray end on. So now the light's coming straight at you, and you're looking at the electric field. If your light's coming straight at you, you can see that there's two polarization states. One corresponding to the electric field going up, down, the other going left, right. So this is just a different way of viewing it, as if the light was heading right at your head. The first thing you have unpolarized light. What is unpolarized light? Unpolarized light is light that's a mixture of the two states. And not only is it a mixture, but the mixture changes with time. It sort of randomly fluctuates between the two states. So if you look over any kind of reasonable time, you get an average of the two, and the light's totally unpolarized. There's no specific direction for the electric field. It goes mix, back and forth through the two states. Most light that you'll see is unpolarized light. It has this kind of behavior. You can pass light through a material that's called a polarizer. So here you have your unpolarized light. The electric field's a mixture of the two different states. And you pass it through this thing, which is a polarizer, which what it'll do is it'll absorb one polarization of the light, one polarization state. In this case, it'll absorb the light that's going up and down, and it'll allow the light that's going back and forth, left and right, to pass through. This little line that's here in the polarizer shows you the direction of light that gets through the polarizer. So when you get to the other side, you now have linearly polarized light. That is, you only have light going back and forth, left and right. You have none of the light that's going up and down. So this is what we mean. Usually if we say polarized light, we mean linearly polarized light. You only have one of the two polarization states. Let's look at that in a little more detail. And again, we're looking at it as if the light's coming straight out of the paper into you. Before you sent it through the polarizer, you had two mixture of polarization states. So it's kind of a random mixture, but at any given time, you have electric fields going horizontal and vertical, and they combine to give you some electric field. And if we assume these two electric fields are the same strength, we'll get an electric field that's larger. If each of these electric fields is E, then the vector sum, will have a length square root of 2 times E, and will be going in the 45-degree direction. The intensity of light is proportional to the electric field squared. And since this has a square root of 2 in front of it, if you square that, you'll get an E squared, and the square root of 2 will become 2. So this intensity, this initial intensity, corresponds to something that's the strength 2E squared. Now what happens after the polarizer? Again, the light's coming straight at us now, and it goes through the polarizer, and afterwards, now you only have the electric field that's going back and forth. So the intensity is going to be the square of this. It's just going to be electric field E squared. This is half the intensity over here. So the intensity now has gone down by a factor of 2. So you take unpolarized light, you send it through a polarizer, and what you get is polarized light, and the intensity of that light is down by a factor of 2. Let's do something a little more complicated. Let's take two polarizers. So you start with unpolarized light. Electric fields goes in every direction. You pass it through a polarizer. Just a second, please. Pass it through a polarizer, and now you have linearly polarized light. Half the intensity is gone. Now we're going to pass it through a second polarizer. This polarizer is going to have its axis aligned the same as the first polarizer. So it will absorb any vertically polarized light, but there is none. And it will pass any horizontally polarized light, and all this light's horizontally polarized. So if this polarizer is present, it'll do nothing. You'll just get linearly polarized light of the same intensity out. Assuming this is a perfect polarizer, which is transparent but absorbs only in one direction. So this is two polarizers aligned, does nothing. What if we rotate that second polarizer? So this starts the same, unpolarized light, intensity I0, goes through the first polarizer, it removes the up and down electric field, half the intensity. But now what's different between the last picture is we've taken this polarizer and rotated it so that it will pass light that's going up and down, but it will absorb any light that's going back and forth. But all the light's going back and forth, so it all gets absorbed. There is no light going up and down because this was linearly polarized. So there's no light that goes through, and you have what's known as crossed polarizers. Crossed polarizers blocks out all the light, and you have nothing coming through. So we see it's very sensitive to how the two polarizers are aligned. Let's look at the general case. The general case, you have your unpolarized light, intensity I0, passes through your polarizer, same as before. You now have polarized light, linearly polarized light. It's going back and forth, nothing up and down. It's got an intensity I0. Now the second polarizer, you're going to rotate. You're not going to rotate all the way so they're crossed. You're going to have the original direction, which is this dashed line, and you're going to have your direction that lets light through, and they're going to be separated by angle theta. It's a little hard to see, but that's an angle theta right there. So what comes out after the second polarizer if it's at an angle theta? So that's what we want to figure out. So let's analyze the electric fields in that case. Okay, here is the light that's been linearly polarized, so it's just going back and forth, back and forth. This is what happens after the first polarizer. Now, the second polarizer is going to be oriented at some angle theta, which is along this dashed line right here. You can write any vector as the sum of two components perpendicular to each other. That's not physics, that's just math. You can write this vector as a component that's parallel to the dashed line, E parallel, and a component that's perpendicular to that dashed line, E perpendicular. That's just resolving a vector into components. And this angle theta here is the angle between the horizontal and the axis of in the polarizing material. Well, this is just now a triangle this is perpendicular and parallel, so that angle is 90 degrees by construction. That angle is theta. So we can find that the adjacent angle, E parallel, is equal to the hypotenuse, E times cosine of theta. So you get E parallel is E cosine theta. The intensity goes as the square of the electric field. So what you find, since the polarizer is only going to pass light that's along this parallel line, it's going to absorb the perpendicular component. So after it goes through the second polarizer, this perpendicular component is gone, and you just have this component, E parallel. And the intensity then is the square of this, which will give you the intensity after it goes through the polarizer is equal to the intensity before times cosine squared of theta. This cosine squared theta law is what's called Malus's law, and that's the law that tells you how much light gets through the second polarizer. Let's see if this is consistent with what we had before. What we had before is if theta was equal to 0, that is, the angle of passing of the polarized light is the same in both the first and second polarizer, then you get cosine of 0 squared. Cosine of 0 is 1, 1 squared is 1, all the light gets through. So the intensity afterwards is equal to the intensity before. That's consistent with what we said, making just qualitative arguments a moment ago. If theta is 90, now you have crossed polarizers. The axis of one polarizer is rotated 90 degrees relative to the other. And cosine of 90 is 0. 0 squared is 0. What you have is, after the second polarizer, you have 0. Crossed polarizers, no light gets through. So that is the behavior that we saw when you had crossed polarizers. In the general, you're going to have some of the light get through. So it goes as cosine squared. So let's see how that behaves. This is a plot of I after is equal to I before cosine squared theta. That's the law of Malus. So what I'm going to do is I'm going to plot the ratio of I after over I before as a function of theta. So all I'm really doing is plotting cosine squared theta. At 0, you have 1. That's when their axes are aligned. At 90, you have 0. At 180, you're back to 1 because cosine of 180 is minus 1, but minus 1 squared is 1. If you go to a 45-degree angle, you're going to find the cosine of 45 degrees is 1 over the square root of 2, or about 0.7. But you square that, and you'll get 1/2. So it's 1/2 at 45, 1/2 at 135. It's not a straight line connection. It's got this cosines type shape. So what you're plotting here is how much intensity gets through as you rotate those polarizing sheets. Okay, well, I brought home from the physics department some polarizing sheets. Here's one of them. Now notice that this is not perfect polarizer because it's kind of dark. So some of the light is just absorbed for any polarization. But it depends it does give you polarized light. How can you tell? Well, okay, first of all, unpolarized light, you remove half the intensity, maybe a little more than half in this case. But I have a second polarizing sheet here. It also does the same thing. It removes half the intensity. If I put them on top of each other, well, you still get you get a lot of the intensity cut out, but not all of it. But I rotate them, and it gets down to 0. It's kind of hard to see because I'm getting a lot of reflections and things. What I want to do is rotate my computer so I'm facing my spotlight here. I got my light that gives me good video. And now I'm going to put a piece of polarizer in front of the light. You can see some of its light's removed. It also scatters a little bit. That's just something that happens. Then I'm going to put another polarizer in parallel to it. And it's still the light's getting through. Now I'm going to rotate. So I'll let you see. I'm rotating this one up. And I can rotate. As I rotate it, you eventually get to a point where, if I can get my hands all aligned, crossed polarizers let none of the light through. So I rotate it around, and some of the lights get through. I want to stay away from that little tag. How do I get rid of the tag here? There. Okay, here's the first polarizer. Here's the second. And as I rotate the second, I'll go through 0 light, and then it'll begin to grow, and I get it to where it's parallel, and all the light gets through. And then as I rotate again. So this is looking at polarization through polarizers. In the next lecture, we're going to look at some more properties of polarization and see how you can get some